So I'm going to take this polar lesson, and the A is going to be polar coordinates with derivatives, and the B will be polar coordinates with integrals. Okay, so we're going to cover both. As long as your calculator is in radian mode, there's not a whole lot. I'm not going to test you on the different polar shapes. Okay, there are lots of really beautiful polar shapes, but that's not going to be the point. The point we're going to talk about is how do we find the slope on polar shapes, and then when we do integrals, what are we going to be finding about polar shapes? The area of polar shapes. So that's what we're focusing on, slope and area. Okay. All right, we do need to have an understanding of how to flip-flop back and forth between how do you make something that's polar versus how do you make something that would be rectangular or Cartesian. All right, so when they talk about rectangular, they're meaning the Cartesian plane using x and y. And then how would you make that equal to a polar coordinate? So a polar coordinate, you get a radius and you get a theta. Theta is measured the same as all other thetas. It starts at the x-axis and then swings out in a counterclockwise manner, and it's 2 pi to make one full rotation, so that's normal. With r, I caution you, they use r, but I caution you in radius can make you think of what shape? Circle. And what is true about the radius of a circle? It's the same. No matter what direction you go, it's the same. Okay. In polar coordinates, in polar graphs, the radius is never the same, which is how you get the cool daisy shapes and how you get the cool like lima bean shapes and stuff like that. So radius is a little bit of a misconception. I prefer to think of this as the distance away from the origin. They call it r, but it's really the distance away from 0, 0. And in fact, you might even want to preface that by saying it's the changing distance away from 0, 0. It's not a consistent distance. If it was consistent, it would be a circle. Because it's changing, we're going to get lots of different shapes. Some rectangular coordinates are easy to convert because they're right on the polar axis. Okay, so let's look at this first example. It's a pretty basic one. So give yourself a polar axis, but instead of being x, you've got your theta measurement here. Okay, we want our theta in this case to be pi halves. So when we go to pi halves, that's taking out the whole first quadrant. So theta would equal pi halves. So that means then the distance from the origin is going to be on the y-axis. And so the distance away from the origin would be 4. So that would put us at 1, 2, 3, 4. So we'd be sitting here. So that's really easy to make into a rectangular coordinate. So the rectangular is just going to be what x and y value? 0, 4. Okay, so those are easy when they end up on the polar axes. It's easy to make a conversion. Now, when they don't end up on the coordinate axes, then how do you make the conversion? All right, so say for example, you have one where it's out here. Well, then you just think of it as a right triangle when you make the, so you've got your theta and you have your r. And your r is the distance away from the origin, but in a right triangle, what position does r play? R is the hypotenuse, very good. And so if we want to convert, then we think of this as a right triangle, and we want to come up with the rectangular coordinates for x and y. So you're going to use trig in your polar coordinates here. So let's say I was wanting to figure out x in relationship to the theta and the r. So if you're thinking about trig, what's the best, what's going to tie x, theta, and r all together? Cosine. Okay, cosine will, because we want adjacent over hypotenuse. And so we have that cosine of theta would be x over r. And then just simply manipulating that, multiplying both sides by r, that leads you to x by itself being equal to r cosine theta. So you can find the x-coordinate by simply taking r and multiplying it by whatever the cosine of theta is. To find your y-coordinate, it's going to be sine that wraps all that stuff together. So you'll have sine of theta is equal to the opposite over the hypotenuse. So that would be y over r. And then to get y by itself, we would end up with y equals r sine theta. That generalization can work in any quadrant. So no matter if your theta drops you into a different quadrant, theta could drop you in quadrants 2, 3, or 4, the generalization of r times the cosine of theta and r times the sine theta will always give you your rectangular coordinates. So you want to generalize that. The rectangular coordinates will be, the first coordinate will always be r cos theta, and the second coordinate will always be r sine theta. Again, hopefully that connects back to what you think about trig on a unit circle, and you think about, oh, the x-coordinate is always the cosine value on a unit circle, and the y-coordinate is always the sine value. So the same thing in polar coordinates, we're going to have cosine be connected to our x rectangular coordinate, but just by multiplying by r, the distance away. So that's how you convert any polar, any polar coordinate to any rectangular coordinate. Okay, so let's find two different sets of polar coordinates that would equate to the rectangular coordinate of negative 3, 3. All right, so we're going to picture, I always think a good idea is to picture this. Okay, we're about ready to move into derivatives. The thing with polar equations is they don't have any derivatives. You have to convert them into rectangular coordinates in order to find derivatives. Okay, you can't just stay in polar. You have to change it first to x and y, and then all the regular derivative rules apply. Okay, so that's the only, so you know all the derivative rules, you just have to know how to do the conversion first, and they must be converted. So that's the first big thing. I would say here, polar curves must be converted into parametrics, okay? The conversions can happen by simple substitutions. So this is one of the basic substitutions you're going to do, and why. So please just have those, always be recognizing them. Just as you would if you were in an equation and you would see sine squared plus cosine squared, that has been drilled so much into your brain to know that that's replaceable with what value? 1, okay, that's a Pythagorean identity. These are, think of these as polar identities. These are polar identities that need to be so much a part of your conscience that as soon as you see them, you're recognizing them, or if you don't see them, you create them. Okay, that'll be really, really helpful. Also, every time you see an r squared, you can replace it with x squared plus y squared. Very similar to the Pythagorean identity. It comes from the Pythagorean theorem. Or vice versa. Anytime you see x squared plus y squared, you can replace it with r squared. So they both are going back and forth. A tangent is pretty normal and standard. All right, so let me show you what I'm talking about. Convert and find its slope. Okay, so you want to convert this first into its x and its y term. So x equals and y equals so that you can find its slope. So we know that the definition of x is r cos theta, and our r this time is 5 secant theta, that's r, and then multiply that by cos theta. What happens when you multiply 5 secant theta times cos theta? Yeah, and what do you get? You get 5. So that is telling you that the x-coordinate is a single number. The x-coordinate is always going to be 5. That's a constant. Okay, the y-coordinate will be r sine theta. that will be 5 secant theta times sine theta. Okay, what do we get when we multiply those two things together? Tangent, why?
Because it'd be sine over cosine.
It would be sine over cosine, so this is going to be 5 tangent theta. So, if x is always going to be 5 and y is always going to be changing, okay, x is 5, so you find 5, and y is always changing, what kind of a picture or a visual are we getting? Yeah, we're just getting a straight up and down line. I'm staying on x, and I'm going up and down and up and down and up and down. My y value is changing all the time. So we have a constant value and a changing value. You don't need calculus to tell me what the slope of that is. You shouldn't. What is the slope of something that just is going up and down like this? Okay, I would rather you say like undefined. Okay, it's an undefined slope. Okay, 1 over 0. Okay, or anything over 0. It's not just 1 over 0, it's anything over 0. And so my slope would be dy over dx. Turns out to be 0. Turns out to be undefined. Now, what if you happened not to consider that? Okay, what if you happened to not realize that it was a vertical line? So I'm going to write here, because the Cartesian graph is vertical. All right, but say that happened to slip your notice and you didn't actually realize that. Could you still do it the regular way? The answer is sure. You're just going to put the derivative of y over the derivative of x. All right, so what is the derivative of y if y is 5 tan theta? 5 secant squared theta. And then what's the derivative of x? 0. So I still got something over 0. And anything over 0, as long as it's not 0 over 0, because that's indeterminate, but anything else over 0 is still going to be undefined. So it still works, just in case you didn't happen to notice the shape, because you don't always get a nice shape. Okay, let's try another one. Convert and find its slope. Now, one way to do this is to do x equals r cos theta and y equals r sine theta. Okay, so that would be 3 over 2 sine theta plus cos theta over times cos theta, and then 3 over 2 sine theta plus cos theta times sine theta. And then try and simplify that, which it doesn't simplify to anything, and then try and find the derivative. Okay, terrible. So instead, you got to think a little bit differently. Think, okay, I can do it this way. It's like, oh, I can do the quotient rule, but I could do the power rule too, and that's easier. So instead, I want to encourage you to think differently. We want to get, would be great if we could find an r cos theta in this problem somewhere. It would also be great if we could find an r sine theta in this problem right here. My r is right here, and my sine theta and my cosine theta are down in the denominator. Is there any way to merge those two together? Cross multiply. Okay, so the best way, or a different way, which I think is going to be better, is to think of this as r over 1 and then do a cross multiplication. When I do that, I'm going to see 2r sine theta plus r cos theta equals 3. And here's r sine theta, which is what I'm telling you, you got to train your brain, train your brain, train your brain. What can r sine theta be replaced with? Y. And then we have r cos theta, and that can be replaced with x. So we have 2y plus x equals 3. Isn't it a lot easier to find the slope of that? Okay, just like last time, if we recognized it was a vertical line, and it was easier to find the slope this way, now if we know it's like this, we can find the slope of that. We don't even need calculus to find the slope of that, because what shape is this? It's a line, and we don't need calculus to find the slope of a line, okay? We just need to think of it in a different format. What form is better to really pinpoint what the slope is? Not standard, this is standard. Y equals mx plus b. So we could convert this into y equals, okay, if I'm going to put it into mx plus b form, it would be negative 1/2 x plus 3/2. So now we can tell the slope, which is dy dx, is going to be negative 1/2. Now, could I have done the derivative? For sure. You can do the derivative also, and you'll still get the same thing. Now, it doesn't always work out to be really nice things. We had a vertical line, which has a defined slope. We have an undefined slope. We have a linear line, which has a defined slope. They don't always work out like that. Okay, convert and find its slope. Okay, remember, what we want is r sine theta or r cos theta. That's what we are ideally trying to get. Last time, I could get r next to the sine and cosine by cross multiplying because the sine and cosine were in the denominator. So I could just zhoop, go across and distribute. The problem here is I don't have sine in the denominator. All right, is there any other way to get an r introduced into this problem? Say that again?
Multiply by r, square both sides. Multiply both sides by r.
Okay, we don't want to square both sides, but I can introduce an r into both sides with multiplication. Yep. So I can multiply this side by r times r, and I can multiply that side by r. So now I'll have r squared equals 4r sine theta. If you go back a couple slides, well, let's do this one first. So now we've created r sine theta, which can be replaced with y. What can I replace r squared with? If you go back a couple slides on your thing. What was it? X squared plus y squared. Now you just convert it. So this is some kind of a circular shape. Anything with x squared and y squared will be a perfect circle. It's not going to be centered on the origin, but it is a circular shape. I can find the slope of this one. So I need my derivative rules to find the slope. So let's just apply our implicit differentiation and find the slope of everything. So we'll start with the slope, or the derivative of x squared, which we know to be 2x, plus the derivative of y squared. All right, Jonathan, you got the derivative of y squared?
2y dy dx.
Okay, I'm so glad. Good job of remembering that it's also dy dx. Okay, and then on the other side, the derivative of 4y. Okay, Edson, you want to try that one?
4 dy dx.
Yep. So this is called implicit differentiation. Remember that there's multiple dy dx's, so we want to gather them on the same side of the equation. So we'll have 2y times dy dx minus 4 times dy dx, and then that equals negative 2x, which I kick to the far side. So dy dx would be negative 2x in the numerator divided by 2y minus 4. And then I can factor and simplify. And so I'm going to have negative x on the top and y minus 2 on the bottom. And that's how I'll find the slope. All right, any questions on that so far? So a couple things you'll have to have in your bags of tricks. Okay, okay? You'll have the basic substitution of r sine theta, r cos theta. You might have cross multiplying to find r sine theta and r cos theta, especially if you have a denominator, that's good. And then you're gonna have the multiplication of r that'll help you find create an r sine theta or an r cos theta. Okay, so here's a rose, and we wanna find the slope of the curve at a particular point. So we'll need to create and put this into rectangular Cartesian coordinates. All right, so Rain, give me the x coordinate.
Sorry. 2 sine 3 theta times cos theta. Cosine theta, sorry.
Okay. Okay. Why am I not just timesing by r? Anybody have an idea of why I'm not just multiplying by r like I did last time? Because I have sine 3 theta. I don't have sine of plane theta. I need sine of plane theta, so that bars me from doing that strategy. So I have to create my x and my y. Okay, all right, Juliet, get me the y coordinate.
2 sine 3 theta times sine theta.
Okay. All right, so then I'm gonna have to get my slope by doing dy over dx, which is gonna be long. Why is it gonna be long? I'm gonna have to do the product rule in both of them. Okay, but then I get to plug pi 6 in with my calculator and I'll be fine. So I'm gonna have to do the product rule here. So my product rule, I like to start with sine theta, and then I'll have 2 cos 3 theta, and then I can't forget the chain rule of 3. And then I'll add to that the other derivative, so 2 sine of 3 theta times the cosine of theta. So that's just the product rule for the y part of our definition, and then for the x part of our definition, we'll have cos theta times 2 cos 3 theta times chain rule of 3 plus 2 sine 3 theta, and then times negative sine theta. And then at that point, you're just going to drop pi 6 into everything and then see what you get. So sine of pi 6, which you should know from the unit circle. So sine of pi 6, that's a half. And then I'm going to take my 2 and my chain rule of 3 and make that a 6. All right, what happens when I plug the pi 6 into something that has that 3 in it? It becomes pi halves, so I need cosine of pi halves. Oh, what's nice about the cosine of pi halves? 0, sweet. So I'm gonna get 6 times 0, which will wipe that all out. Okay, on the other side, or the remaining part, I'll have 2 times the sine of pi halves, which is 1, times the cosine of pi halves again, cosine of pi 6ths, which is rad 3 over 2. So my numerator is actually a lot simpler than what I thought it was gonna be. My denominator will have rad 3 over 2, but then it's going to have 6 times 0 again, which will wipe that out, which I'm grateful for. Then I'm going to have negative 2 times the sine of pi 6ths, which is 1/2, and then times the sine of pi halves, which is 1. So it did simplify quite a bit for me by wiping out those zeros. What else is nice about the simplification that can happen right here? Besides the 0 knocking out all this. The 2 here and the 1/2 will simplify, and the negative 2 and the 1/2. So I really end up with, the only thing left is negative rad 3. has that.